So I have this flow chart on my website. It's linked, ivanlee.com, of course, for those of you guys. At this point of the semester, if you're still watching these videos, you probably know my website. But again, it's in the description. Anyways, there's this chapter 16 flow chart that I want to go through before we get to 16.7. And I'm going to go get through 16.7 real quick here. So essentially, it shows you like which Green's theorem thing to work with, which theorem to work with, given your certain circumstances, and yeah. So right. So if you're asked to find a line integral, f.dr, check for path independence. If not path independent, then you want to use this flowchart. And oh, excuse me. So here's the flow chart, right? So this first question up here, you're asked if it's closed or not. And so what does that mean? Well, so either your region has to be closed, right? Your curve has to be closed. So in case of flow, line, work, and circulation, which are all the same thing, f.dr has to be on a closed curve. And so when we look at Stokes' theorem right here, right, it's a three-dimensional line integral, and it has to be on a closed curve. So let's hop in then to 16.7, which is Stokes' theorem, and I'm going to be splitting this section up into two videos. The first video, so if we remember what that was, we had really f.dr, right? And there really should be a circle there because it has to be a closed curve, right? It has to be over a closed curve. And then if it was three dimensions, we use Stokes' theorem, which is then it's equal to the double integral of del cross f dot n d sigma. Okay. So what does any of this really mean? Okay. So again, closed curve is the first one, and then yeah. So first, del is going to be the vector partial of x, comma, partial of y, comma, partial of z. All right, and so del f, right, which is del of a function, right, is, well, remember it was just the partial of df dx, df dy, df dz, right? Remember that was del f. So without the f, then we just have partial x, partial y, partial z. All right. And cross is your normal cross. F is a vector field, so let's put that guy up there to indicate that. Well, let's not. I mean, F has always been a vector field, right? F is a vector field, 3 dimensions, right? Since we're in 3D. N is your normal vector, and d sigma. D sigma comes from then 16.5, where we had those 4 formulas for d sigma. And there's going to be 2 videos that I'm going to do. The first video, which is this one, comes when they ask you to evaluate this. So if you're asked to find this, if you're asked to find f.dr, you use this guy, right? And then if you're asked to find curl f.n d sigma, so this is called curl. All right, that's called curl. So if I'm saying curl f.n, that's what that is. If you're asked to find curl f.n d sigma, so if you're asked to find this, then you use the line integral. Or there's another way you can do it, or independence of surface. But anyhow, right, these are our 2 videos. So this is going to be the first video in this section, and then this over here is going to be video 2. So let's jump into the problem then. So we're asked to find a line integral, and we use Stokes' theorem to find that line integral. So this comes from 16.7. It's actually example number 4. So the book actually does it out, but I want to verbalize it for you guys in a video, just so that you guys know what's going on. So let me pull up the video. Let me pull up the problem on my end. I have it written down, but I want to make sure that I have I read it exactly from the textbook. Okay. find the circulation. Oh, that's not the right one. I said example 4. Maybe. Is it 9 that I'm talking about? Ah, it is 9. Okay, I can't read my own handwriting. 9 looks like a 4. Anyways, example 9. Example 9. Example 9. Okay. Use Stokes' theorem to evaluate the line integral, f dot dr, if f is equal to xz, xy, 3xz, and c is the boundary of 2x plus y plus z equals 2 in the first octant. Traversed counterclockwise. All right, so again, you want to make sure that when you're doing a line integral, you want to be counterclockwise. And there's a picture that we can, it's included in the book, but I'll draw it here. Right, so what is this? Well, 2x plus y plus z equals 2. So we essentially have the points, right? We have 1, 0, 0. Okay, and then we have y equals 2. So this is z. So x, y, z. So and then we got z equals 2, and then we also got y equals 2. Right. So I got this plane right here. Okay. And yeah, and what? Well, we're going counterclockwise, so we're going like this way. Okay. And sure. I mean, right. So okay, that's it. So what did I say? Well, if we want to evaluate, right, if we're asked to find f dot dr, then we want to use Stokes' theorem, which is the double integral over the region of curl of f dot n d sigma. So what is this? Well, that means we need to find each individual thing, right? And the first thing we need to find then is curl f, all right? So what is curl f? Well, remember, this del guy, this upside down triangle, is partial x, partial y, partial z. So I'm actually doing ijk partial x, partial y, partial z of f. And remember what f was? F was xz, xy, 3xz. All right, and so this cross product, right? This is a cross product. Del cross f is curl, all right? It's called curl. So this is a name you really need to be familiar with. It's called curl, not Carl. Curl. So del cross f, and this becomes, all right, so yeah, cross out that guy. You get partial of y, 3xz, minus partial of z, xy, all right, comma. Then you get negative partial x 3xz minus partial of z xz, and then you get comma partial of x xy minus partial of y xz. All right, and what is this? Well, partial of y of 3xz, that's 0, and then partial of z of xy, so I'm looking at this first guy, is also 0, so you get 0 minus 0, that's 0. All right, here, partial of x of 3xz, so that's minus 3z. So you get minus, you get 3z, and then you get minus partial z is x, so you get negative 3z minus x, and we'll flip that around a little later. And then over here, partial of x is equal to y, and partial of y of that guy is equal to 0. So, so if you really want to write it without any minus of a product or minus of a sum or a difference, this becomes right x minus 3z and y. Okay, so that's how you calculate the curl. All right, we're cool. We're cool with that, right? And now what? Now we need to find the normal, right? We need to find the normal. And what's the normal vector? Well, the normal vector is we're on the plane, right? So when we're given a plane, the boundary of the sky is really the boundary of the plane, and so on the plane we have a normal, and we all should remember how to calculate the normal of a plane. normal is equal to then of this guy, right, is equal to 2 comma 1 comma 1. But we want the unit normal, so we need to divide it by the magnitude. So 2 squared plus 1 squared plus 1 squared, and this is really 2 comma 1 comma 1 over root 6. All right. Okay, and now what? Now I need to find d sigma. And how do we find d sigma? So there's actually two things we need to do here. What happens is when you have Stokes, when you have a region like this, we want to project this region into one of the planes. So for example, since we're all familiar with the xy plane, I only want to look at the area of this region, essentially the shadow of this region in the xy plane, okay? And so now if we project that into the xy plane, what happens? Well, what happens is any z's we have, right? So any z's we have here, they need to be replaced by x's and y's. And so since this is my equation, 2x plus y plus z is equal to 2, I can also rewrite it as z is equal to 2 minus 2x minus y, right? So here, this also then needs to be replaced with 2 minus 2x minus y. All right? And we'll figure out exactly what that is a little later. But again, that's because we're shadowing our region. We're shadowing this this plane, right, that we're traversing. We're shadowing into the xy plane. So z isn't there anymore, right? We don't have z anymore if we're only considering the shadow. And so z then needs to be described in terms of x and y. Okay, so that's the first step. The second step is then to complete the shadowing, we want d sigma to be something. Well, d sigma then, it makes sense to describe it implicitly in for two reasons. The first reason is because this guy is obviously a function of x, y, z, and then here is a constant on the other side, right? And the second reason is because if we're shadowing onto the xy plane, it's very obvious what we choose our p vector to be, which right, remember the p vector is like the one vector that's like super like not intuitive. Sometimes you just guess it to be something because you want to be in the xy plane. But here, since we're shadowing into the xy plane, then we're going to let d sigma equal the magnitude of f over the magnitude, the gradient of f, the magnitude of the gradient of f, and then we got the gradient of f dot p, and then you take the absolute value of that, right? So this is the implicit. This is the implicit one from 16.5, right? So this should look familiar. And because we shadowed into the xy plane, again, look at the red, right? We shadowed into the xy plane. P is equal to 0, 0, 1, right? Because we're in the xy plane. So then what we want to do now is we want to take the gradient of this guy, of 2x plus y plus z, because that's my region, right? And that's going to be f. And so, well, we actually kind of did that already. It's a 2, 1, 1. Right, and then and now we take the magnitude of that, and now we want to take gradient of f dot p. So this is the absolute value then of 2 comma 1 comma 1, right, dotted with 0, 0, 1, which is p, and I get root 6 on top, and on the bottom I get 1, and so d sigma is root 6 dx dy, right? Because again we shadowed into so these guys need to have dAs on them. And dx dy is dA because of my choice of p, right? So p is equal to 0, 0, 1 because we shadowed into the xy plane. All right. And, okay, so now I have curl of f, I have n hat, and I have d sigma. And now I just plug it into the equation, right? So the line integral then, the line integral f dot dr is equal to the double integral of curl of f, which is del cross f dot n d sigma, which in our case is, well, curl of f is 0 comma x minus 3 times 2 minus 2x minus y, oh boy, and comma y, dotted with n, which is 2 comma 1 comma 1 over root 6, and then d sigma, which is root 6 dx dy, right? And or I mean, it doesn't matter. Let's write a dA for now. So this is dx dy or dy dx, right? Right, because I need to figure out my bounds anyways, and we're not quite there yet. So now, okay, so now what? So now I got the double integral over my region, or double integral, and then this dot product becomes, well, these guys canceled, right? The root 6 is canceled, well, that's good. So now I just dot it with 2, 1, 1, and so I get then x minus 3 times x minus 3 times 2 minus 2x minus y, and then plus y dA. And so this is the double integral then of x minus 6 plus 6x plus 3y plus y, and so we get dA. And so this double integral is 7x plus 3y minus 6. All right, and now we need to figure out what dA is, right? I need to figure out what dA is. And so remember, I'm shadowed in the xy plane, right? I'm shadowed in the xy plane, which is that red area. So in the xy plane then, so now we want to find dA, dA bounds, right? So remember, my equation was 2x plus y plus z is equal to 2, but in the xy plane, oh boy, this. So find dA bounds. We had our surface was 2x plus y plus z is equal to 2, but we're in the xy plane, which is z equals 0, so I get 2x plus y is equal to 2, which is the line then y is equal to 2 minus 2x, right? So if I draw my region in the xy plane, so first of all, I'm bounded in the first octant, right? So which means x, y, and z all have to be greater than or equal to 0, and so I'm bounded here, and well, that doesn't matter. And then I want to draw y equals 2 minus 2x, which happens to be like that line right there, right? So that's 1, that's 2, so that's 2 minus 2x, and then this is my region, since I'm bounded by y is greater than 0 and x is greater than 0 because I'm in the first octant. And okay, and now I just need to figure out my order of integration. Well, since this is y is equal to 2 minus 2x, it makes sense then if I integrate with respect to dy first, right? Remember this, right? So I hit 0 and then I hit the line, and so then my integrand here, I would want to do dy dx, and then dy would go from 0 to 2 minus 2x, and dx then, the minimum value is going to be 0, right, because I'm in the first octant, and the maximum value, as we can see in this region down here, is going to be 1. And so this is my integral, and if I evaluate this integral, you should get the following answer. You should get -1 as the line integral. So so the line integral of going around this picture right here in that direction is the line integral is -1. And you could have done this by parametrizing the 3 line integrals and adding them together. Nothing wrong with that. But yeah, Stokes' theorem. And again, remember, the first thing we have to check is this region closed or not, right? And we can see here that obviously we have a triangle, which that's a closed line, right? It's a closed curve. So, all right, that's this first video then. Again, we were asked to find this the line integral f dot dr, and so we use Stokes' theorem to find the line's integral, or we use curl of f dot n d sigma to find line integral. The key takeaways: we found curl, we projected into the xy plane, which is that red area, and by doing that, by projecting into the xy plane, then z had to go away, so then we had to replace z with something. You can project into other planes, so don't let the xy plane be the only plane you want to project into. We could have projected into the zy plane, which is this yellow guy that I'm shading right now in the back, right? You could have projected into that plane, but then just keep in mind then that there's going to be no x, so then we would have had to replace the x there, and then of course then your implicit surface, you have to choose your p accordingly to wherever you project your region onto. All right, so again, we projected on the xy plane because everyone's familiar with that, but you know, it might be quicker to project onto other planes, who knows. And then, yeah, so look, this essentially brought back everything, right? This is such a great chapter because it brings back everything we've learned so far. It brings back the cross product from chapter 12. It brings back how to find the normal from a plane, which is chapter 12. And we have gradients involved. We have d sigma, which is from 16.5. So we got chapters 14 in here. We got chapter 16.5 in here. And then finally, you got to evaluate this line integral, which is just pure chapter 16 stuff. So, yeah, so again, really good question. You see these all the time on exams. And yeah, so this again was the first video where we went from the line integral to curl of f dot n d sigma. And so in the next video, then we're going to be asked to find this guy, and then we need to use the line integral or independence of surface. So I'll see you guys in that video.